Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to discuss is a class of groups known as the finite cyclic groups. Okay, so in the previous video, what we looked at was the symmetric groups, which was a whole class of groups, loads of different groups. So for instance, we had S1, S2, S3, S4, S5, okay? And they were all created in a similar way. The finite cyclic groups are similar to that. They're a whole class of groups. They're a class of loads of different groups that are all created in a similar way, basically. Okay, right. So we're going to start off by discussing finite cyclic groups in full generality, okay, and then what we'll do is we'll do some examples of finite cyclic groups so that you can get the idea of what these really are. Okay, right, so just like the symmetric groups where we had S1, S2, S3, S4, S5, S little n, where n was any natural number, the cyclic groups are the same. You have C1, C2, C3, C4, C5, C little n basically, where little n is a natural number. So there are lots of different finite cyclic groups where this little n can vary over any natural number, okay, and all of the finite cyclic groups are one of those, basically, C1, C2, C3, C4, C5, on and on and on. Okay, right, so how do we create these cyclic groups then, these finite cyclic groups? Okay, well, when we were discussing the symmetric groups, S little n, we saw how the way that you created those was by thinking of a set containing little n elements and then looking at all possible set permutations of that set containing little n elements, okay? And then the group was just give every single set permutation a symbol, a name basically, put all of those symbols into a set, and then have a composition law on that set, and the composition law is going to be basically compose the two set permutations that the symbols represent, and then what set permutation do you end up with? That will be the answer to those two symbols composed with one another basically. And we're going to do a very similar thing for the finite cyclic group. So once again, what we're going to do, if we want to think of the cyclic group C little n basically, again what we need to look at is the set containing the elements 1, 2, 3, all the way up to little n. So you could imagine that little n is equal to 7 maybe, okay, and then we'd have 1, 2, 3, 4, 5, 6, 7. Or if little n was just equal to 1, we'd just have the set containing 1, okay. If little n was equal to 2, we'd just have the set containing 1 and 2 basically. Okay, so when you want to create the cyclic group C little n, you need to create this set 1, 2, 3, all the way up to little n, containing all the natural numbers up to and including little n, basically. Okay, right, and then what we're going to look at is set permutations of this set, just like we did for the symmetric group S little n. However, we're not going to look at absolutely every single set permutation of this set this time, okay? So S little n, what we did is we looked at every possible set permutation of this set containing little n elements. We gave every single one of those a name and put it into the S little n group, basically the symmetric group on little n elements, okay? In the case of the finite cyclic group C little n, we're not going to look at every single set permutation. We're going to restrict our attention to what are known as cyclic permutations. Okay, right, so what I want to now explain to you is how you can intuitively think about cyclic permutations. So the best way of thinking about cyclic permutations of this set of little n elements is to think about having a disk which is free to rotate in a two-dimensional plane, and then think about putting these symbols around the edge of the disk. So let me just do this. Okay, so here is my disk. Okay, not particularly well drawn there, but there is my disk. So imagine that it's a perfect circle, okay, and it's a two-dimensional disk, and imagine that I'm going to put a nail down the middle here, right at the center. So what I'm going to do is nail it down onto, let's say, the table below. Okay, so I've nailed my disk down to the table below, and all I can now do with this disk is I can spin it round, basically. Okay, and this is where the concept of cyclic comes from, okay, because we're going to be cycling our disk here. Okay, right, so all I can do with this disk is now rotate it around. I am not allowed to break the nail, basically. I'm not allowed to pull it off the desk and move it around in three-dimensional space. All it can do is rotate around in the two-dimensional plane that it's now attached in, basically. Okay, right, so now what I'm going to do is I'm going to put these little n elements around the edge of the disk. Now, you could do this in an arbitrary way, however, it's easiest just to do it in an ordered fashion and to do it clockwise. So what I'm going to do is I'm going to put the elements of my set here, 1, 2, 3, all the way up to little n, around the edge of the disk, and I'm going to do it in a clockwise way. As I say, you could do it however you want, actually, okay, but for now, let's just say we're going to do it in this ordered way where I put them in a clockwise order and in ascending order, basically, like you'd see on a clock, basically. Okay, now, I want the n little numbers here to be evenly spaced, okay, so I want the angles between them to be the same. So what I need to do is take 360 and divide that by little n. So I'm dividing 360 degrees into little n pieces, okay, and that will give me the angle that I need to have between each one of these elements, basically. So what I'll start by doing is I'll put little 1 at the top here, okay, then what I'll do is I'll have an angle 360 divided by n between that element and then the next element, little 2 here, and then I'll have the same angle between 2 and little 3 here, so this will again be 360 divided by n, and I will continue all the way around until I finally get to little n right over here, basically. Okay, so what I have done is I've put the elements of my set here all the way around this disk, basically. Okay, right, so the cyclic permutations of this set of little n elements are the permutations that can be achieved just by rotating this disk. Okay, and this is not going to include all possible permutations, at least not if n is some large number. Okay, if it's 1 or 2, if little n is 1 or 2, then actually it does end up including all permutations, simply because there are so few permutations of those sets. However, if n is 3 or bigger, we're not going to get every possible permutation that was represented in the symmetric group S little n. Okay, so now from 3 upwards, the cyclic group Cn is going to be different from the symmetric group Sn. Okay, right, so basically what you're allowed to do then is you're allowed to rotate this disk around and see which permutations you can build by rotating the disk around. Okay, so let me show you what I mean by this. So, one permutation then would be rotate the disk by 0 degrees, don't rotate the disk at all. Okay, what does that do? That sends every element to itself, every element stays where it is. Okay, so that's going to correspond to the identity permutation, so let me just write this out. So we'll have 1, 2, and then we'll have all up to little n here, and now if we don't rotate it at all, then everything will go to the same element, basically. 1 will go to 1, 2 will go to 2, 3 will go to 3, and of course little n will go to little n, so all of the elements stay the same. Okay, so rotation by 0 degrees is the identity permutation, basically. Okay, right, then what we can do is we can rotate by 360 divided by n degrees. Okay, that will map 1 onto 2 basically, because now what we'll do is we'll rotate the whole disk like this. 1 will go to where 2 is, 2 will go to where 3 is, 3 will go to where 4 is, 4 will go to where 5 is, etc., all the way down to where, when little n minus 1 goes to where little n is, and little n goes to where 1 is, basically. Okay, so this is why these permutations are called cyclic permutations, because they can be thought of just as the rotation of this disk, basically. So let me just write what that permutation out will be in this form over here. So I'll put all my elements here. 1, 2, 3, all the way up to little n. 1, 2, 3, all the way up to little n. So 1 will go to where 2 is, 2 will go to where 3 is, 3 will go to where 4 is, little n minus 1 will go to where little n is, and little n will go to where 1 is. Okay, so that will be rotation by 360 divided by n degrees. Now, of course, we could rotate by a bigger angle than that. We could rotate by 2 times that, and that would be the permutation that sends 1 onto 3, 2 onto 4, 3 onto 5, etc. Okay, and then you could go bigger angles. Okay, so all of those possible rotations, basically, they are going to represent cyclic permutations. So by rotating the disk by different angles, you can create different cyclic permutations. And basically, the concept of the finite cyclic group C little n then is to create a disk like this, where you put the little n elements around the outside of the disk. Okay, you create all of these permutations that can be thought of just as rotations of the disk, okay, and you then give those symbols. So I'll give each of these a symbol. So I could call this one, for instance, the identity. I could call this one sigma, okay, for a rotation. And you give every single one of the rotations a symbol, and often you will express all of the other rotations in terms of this fundamental rotation. Okay, what do I mean by this one? Well, sigma is the rotation by 360 divided by n, the smallest angle that actually you could rotate it by and actually achieve a permutation. And I should stress that if you rotate by something smaller than that, obviously that's not going to actually be a permutation at all, because you're not actually going to map elements onto each other, basically. So you do need to rotate it by a multiple of this, otherwise it doesn't make sense. Okay. But what do I mean about all of the other cyclic permutations being expressed in terms of this one? Well, basically all the others are just multiples of this one. Okay, if you do this one a certain number of times, you can get any of the others. So for instance, rotation by 2 times 360 divided by n, all that actually is sigma done twice. If you rotate by 360 divided by n twice, that's the same as rotating by 2 times 360 divided by n. So actually all the other rotations by multiples of this angle are just doing this a certain number of times, basically. So for instance, you can represent the rotation by 2 times 360 divided by n degrees as just sigma squared, basically. Again, I think I'll just write that one out. So if we just write it out quickly here, so here is our set, okay, and we'll have 1 going to where 3 is, 2 will go to where 4 is, 3 will go to where 5 is, okay, little m minus 2 will go to where little n is, little m minus 1 will go to where 1 is, and little n will go to where 2 is. And that actually is just doing this twice. So if you do this and then do it again, the net result is that you get this, basically. And that's what I mean by saying that every single one of the other rotations can just be expressed as this to a power, basically. Okay, right. To create the finite cyclic group Cn, what you do then is you create this set 1, 2, 3 all the way up to little n. You imagine sticking them around a disk, around the edge of a disk, and then you create the permutations, which are called cyclic permutations, which can be thought of as being rotations of this disk, basically. Okay, and then the composition law on these permutations is just going to be composition of the set permutations together. So in this group, you'll give every single one of these cyclic permutations a symbol, and then you can define a composition law on that set of symbols. And just by remembering that they represent these cyclic permutations and thinking of composition just as composition of the cyclic permutations, and then remembering what symbol that new result, the composition of the 2 cyclic permutations, is represented by. Okay, right. So I want to ask some questions then now. What I want to ask is, why does this form a group? Okay, and also how many elements are there within these groups? So what is the order of the arbitrary group C little n, basically? Okay, right. So first let's discuss why this is actually a group. So why are these finite cyclic groups actually groups? Well, let's remember the axioms that you need to obey in order to be a group. Okay, so firstly, you need closure. Okay, you need to make sure that when you take any element within your group and you compose it with any other elements. So if you take any two elements, let's say little x and little y, which is an element of our finite cyclic group C little n, we need to make sure that x composed with y is also an element of C little n. Okay, so remember, how do we compose the elements of C little n together? Well, the elements of C little n are just symbols representing these cyclic permutations. So the way that we compose them together is thinking about composing the cyclic permutations together, and what then is the answer? Well, if it's going to be closed, if the group is going to be closed, then we better hope that when we compose two cyclic permutations together, we get another cyclic permutation, because only then will the answer to the composition of the two cyclic permutations actually be another cyclic permutation, and therefore it will be another symbol that's represented in Cn. Okay, so we need to make sure that when we compose two cyclic permutations together, we end up with another cyclic permutation. Now, hopefully that should be pretty obvious, okay, because the cyclic permutations, remember, are rotations of this disk. We can think of them as rotations of this disk. If we rotate the disk and then rotate the disk some more, which is what we mean by composition of two cyclic permutations, then we end up still with a rotation, basically. Okay, you don't suddenly end up with something that's not a rotation when you compose two rotations together. So, for instance, if I compose sigma with sigma squared, that means rotate by 360 divided by n, and then rotate by 2 times 360 divided by n. Okay, I end up rotating by 3 times 360 divided by n. Okay, so basically what I'm trying to say is that whenever you compose two cyclic permutations together, which you can think of as the rotations of this disk, you end up with another cyclic permutation, and that will be represented within this set of symbols, and therefore whenever I compose two arbitrary symbols together in this group, I will end up with the answer being another symbol within the group. Okay, so basically everything works fine. The composition law will be closed, basically, because whenever I compose two cyclic permutations together, I end up with another cyclic permutation. Okay, right, so that's closure made sure of. Okay, next up what we want to look at is associativity. Okay, the most subtle of the group axioms. Now, we get associativity because, again, we are just thinking about the symbols of our group as representing set permutations, and we know from our in-depth discussion in the video on the definition of a group that whenever you think of the elements of your group as representing set permutations of some set, okay, and then the composition of the elements of the group is just representing the composition of the set permutations which they represent, then you instantly get associativity. That's where associativity really comes from. Okay, so we know that it's going to obey associativity because we are thinking of the elements of the group as representing set permutations and the composition as representing the composition of those maps. Okay, so we instantly can tick off associativity. Okay, if you want a more in-depth discussion of that and you haven't watched my video on definition of a group, we go into that in a huge amount of detail in my video on definition of a group. Okay, right, so the third axiom of group theory then, we need to have an identity element within the group. We need an element which will compose either on the left or the right with any other element just to give that arbitrary other element back again. Okay, and we know that in terms of thinking about the elements of a group as representing set permutations of some set, what that means is that we must have within our group a symbol representing the identity map. Okay, now I've said that we will always have that because we always have the option of rotating by 0 degrees. Okay, so the identity map is always a cyclic permutation, basically, of the set. Okay, so we will always have within our group Cn a symbol, which will often be represented as little I here, which will be representing the identity map, basically, and we know that this will compose with any other set permutation, including all of the cyclic set permutations, which are other elements of our group, to give that other set permutation back again, and that means that this identity element will compose with any of the symbols within our group just to give those arbitrary symbols back again. Okay, so we do have an identity, and fourth and finally, the final axiom of group theory is that we need inverses. Okay, so basically for any element of the group, let's say any little g is an element of, I'll put c little n, okay, so for all, I'll put a little bit of fancy maths symbols there, so we'll have for all little g is an element of c little n, we need there to be another element, g inverse. Okay, there needs to exist a g inverse as an element of c little n, such that g inverse, so the composition of g and g with g inverse, and also the other way around, g inverse little g, okay, is equal to the identity basically. Okay, so what this says in terms of set permutations is that if you have any set permutation represented within your group here, so if you have a symbol representing a certain set permutation within your group, you need to have another symbol representing the exact inverse map, the map that reverses that set permutation. Okay, so whenever you have a set permutation, the inverse map is also going to be a set permutation. That's just a property of bijections. Okay, and those two will be able to compose with one another to give the identity map, to give overall do nothing basically. Okay, and it works either way around that you compose them basically. Okay, so what we need to make sure is that for any set permutation that we have represented within our group c little n, that we have another symbol representing the inverse map basically. Okay, so we know that this group c little n has a symbol representing every single cyclic permutation of this set of n elements basically. Okay, so what this amounts to is that we need to check that the inverse set permutation of any cyclic permutation is another cyclic permutation, and indeed that is true. And let me explain why. Okay, right, so for instance, let's just take the example of this sigma element here, which is this element where we rotate by 360 divided by n degrees. Okay, basically the inverse to that is also going to be represented within our group, and the reason is that we can just take the element n minus 1 times 360 divided by n. The element which represents the cyclic permutation where you rotate by n minus 1 times 360 divided by n degrees. Okay, now why is this going to be the inverse of sigma? Okay, well, basically, sigma says rotate by 360 divided by n degrees. If we compose it with the element that represents this rotation by n minus 1 times 360 divided by n degrees, then together what they will now do is rotate by 360 divided by n, and then we will rotate by n minus 1 times 360 divided by n degrees. And that will overall mean that how much do we rotate by? Overall, we now rotate by these two added together, which will just give us n minus 1 times this plus 1 times this will give us n times 360 divided by n degrees. I've just added this one to this one. Okay, and of course the n's will now cancel, so we'll get that we have rotated by 360 degrees. Okay, and when you rotate by 360 degrees, that's equivalent to doing nothing. So what I'm saying is the reason that all of the inverse maps exist is that for any rotation, you can just have the other rotation which rotates by the complementary part of 360 degrees basically. So if you rotate by a certain angle, you can just then have the rotation which rotates by 360 minus that angle, okay, and that will return you overall to rotating by 360 degrees, which will then just map all of these elements onto themselves. So that is why whenever you have a cyclic permutation, the inverse set permutation for that cyclic permutation is also another cyclic permutation. Okay, so what I am saying basically is that any cyclic permutation that is represented by a symbol within our group c little n is also going to have another is going to have its inverse represented by a symbol within this group as well, basically. Okay, because its inverse will also be a cyclic permutation, which is represented in that group, basically. Okay, so that's why it obeys inverses. Okay, some other things that I want to do before we have a break are prove that these cyclic groups C little n are abelian groups, okay, and also work out what the order of a group C little n is, so how many elements are in the group C little n. Okay, so firstly, why are these groups always abelian? Okay, so remember, an abelian group is a group which is commutative under composition. Okay, so an abelian group is one where it doesn't matter if you take an element x and compose it with y, or whether you take the element y and compose it with x. The answer is the same, basically. It's one where the composition table is symmetric down that diagonal line. Okay, right. So why is it the case that it does not matter which order you compose elements in these cyclic groups of n elements, basically? Okay, well, the reason is that remember what composition actually means in these finite cyclic groups. Okay, it just means compose the cyclic permutations, which basically just means compose the rotations. Okay, and basically when you rotate by a certain amount and then rotate by another amount, it doesn't matter which order you do those in, because rotation is commutative, because it doesn't matter if I rotate firstly by the angle theta and then by the angle phi, or whether I rotate by the angle phi and then by the angle theta. That means that it doesn't matter which order I actually compose two elements in these groups, basically. Okay, because of the fact that when you compose rotations, that is commutative. Okay, so that's why all of these groups are abelian, basically, why they're all commutative. Okay, right. The final thing that I want to discuss is what is the order of the general C little n group? How many elements are usually in this group C little n? Okay, so let's think, how many cyclic permutations actually are there? Well, all you need to actually tell me to specify a cyclic permutation completely is where the element 1 goes to. Now, what do I mean by that? Okay, well, I mean, once you tell me where 1 goes to in your cyclic permutation, you instantly know where everything else goes to, because if I know where 1 goes, then all I have to do is rotate the disk to get 1 going to the correct place, and then I instantly know where everything else goes. Okay, now that means that I can very easily work out how many cyclic permutations there actually are of the set of n little things, basically. Okay, because there are just n little things that I can send 1 to, and therefore that's all of the cyclic permutations. So basically I can send little 1 to 1, and that's the identity permutation. I can send little 1 to 2, that's the sigma permutation. I can send little 1 to 3, that's sigma squared cyclic permutation. I can send 1 to 4, that's sigma cubed, and I can go on, and I can finally send 1 to n, okay, which is sigma to the power of n minus 1, basically. Okay, right. So that then tells me how many total cyclic permutations there are of this set 1, 2, 3 all the way up to little n. It tells me that the order of this group must just be little n, because basically as soon as I know where 1 goes, that instantly specifies the entire permutation, basically, and there can be no other ones outside of that. So I've only got little n things that I can send 1 to, and therefore I've only got little n cyclic permutations. So the order of the arbitrary group C little n is equal to little n, basically. Okay, so that instantly shows us that this is much smaller than the symmetric group S little n, because remember the order of the symmetric group S little n was n factorial, because in S little n we had every single permutation of the set containing little n things represented. Okay, so remember, what you could do is you could say, okay, I can send little 1 to n different things, then how many different things are there that I can send little 2 onto? Well, there's n minus 1, because I've already given 1 away to where 1 is going, okay? So now there's n minus 1 places where I can send little 2, there's then n minus 2 places that I can send 3, there's n minus 3 places that I can send 4, etc., and it goes on, and that's where you get the n factorial order of the symmetric group, S little n. Okay, so C little n, once you're past n is equal to 2, is going to be smaller than S little n, basically. Okay, right, so we'll call it there for this video, and then in the next video what we'll do is we'll look at examples of finite cyclic groups. So we'll do C1, C2, C3, C4, just to solidify the concepts that we've been through in this video.